Life began in the ocean. We all come from the ocean. And as a species, we rely on the ocean. Half of the world's oxygen comes from the ocean. The ocean influences the climate. And it's full of fish that we as a species, again, rely on. 3.1 billion people get 20% of their daily protein intake from fish. Again, it's a lot of people. And these fish, in turn, rely on complex ecosystems for their own survival. And these ecosystems are under threat by changing temperatures due to climate change, overfishing, pollution, underwater mining, and so on. These complex problems need solutions. That's where my work comes in. I work with the Mindero Foundation Oceanomics Division and many partners, such as industry, academia, community groups, and governments to find new technologies to help the ocean. Our work focuses on environmental DNA, short eDNA. With eDNA, it's very much like with crime scenes, where forensics people go, sample DNA from crime scenes, and analyze that to catch criminals. But we don't catch criminals, we look for fish. There's a lot of fish to look for. Australian oceans are home to 5,000 marine species. Our methods are simple yet revolutionary. We go out on boats, we sample water, we push this water through filters. We give this filter to the lab people to sequence us using DNA sequencing machines. And these DNA sequencing machines generate massive amounts of data. The current generation of DNA sequencing machines generate about 2 to 3 terabytes of data. For the more seasoned among you, that's about 1 to 2 million floppy disks of data. For the younger among you, that's 2 to 3 terabytes of data. And somebody needs to analyze all that data, and that's where my work comes in. I'm a bioinformatician or a computational biologist. I use text comparison algorithms, AI, and supercomputers to make sense from that data, to find the biological meaning in this data. For a typical Australian marine sample, I can find about 200 species of fish. I compare these 200 species of fish with reference libraries of sequenced fish. But we hit limits there too, right? Less than 5% of species have had their genome sequenced. That's the one half. For the other half of species, I use artificial intelligence and machine learning to make essentially educated guesses. For example, if I show it 40 snappers, it can kind of guess what the range is of potential snappers. And from there, it can make an educated guess and tell me for my sample, okay, this looks kind of like a snapper. And from there, we can take the snapper family comparison and drill down a bit by comparing it with known species distributions. And from there, infer where the species are distributed. But how does this differ from established methods? All species shed DNA. You noticed it, right? If you live with long-haired people, you find the long hairs everywhere. It's in your clothes, in your washings, in your dishwasher, everywhere. Fish also shed DNA. What we do is we go in, we pull the DNA from these cells, and from there, map where fish is. Of course, people have forever been mapping where fish live, right? People have been trawling, fishing, diving, taking underwater pictures using remote-baited underwater cameras. How does eDNA differ from these established methods? Scale, scalability. The Australian marine jurisdiction is 8.9 million square kilometers. It's huge. That's 20% of the moon's surface. And we don't have enough people to cover all that, right? We don't have enough divers, obviously. But what do I work on specifically? Imagine you're on a social media webpage, and the platform tracks your likes, your interactions, and your friends. Over time, it creates a digital footprint of you, and it can track your friends, and it can even infer friendships for you that are not explicit. So we have 4 friends, and we can infer a friendship there, even though it's not made explicit. But what about people who don't have accounts? These shadow profiles are made by the social media companies for people who don't have accounts. By analyzing these, in this example, 4 people's interactions, posts, photos, and likes, the social media account essentially can make a 5th shadow profile based on that. What I do is I steal this concept for good. I use it for fish. We might not find the DNA of a fish that was there on the day. It's just random. You might not know this, but 5 milliliters of ocean contain 5 million bacteria and 10 million viruses. We don't need to sequence 100 fish when we can sequence millions and millions of bacteria and viruses. by sequencing and sampling many, many sites and many, many times, we can infer which pieces of non-fish DNA associate with fish DNA. And from there, essentially create shadow profiles of fish. By using these shadow profiles, we can start to make sense. We can find this hidden biodiversity among us and in the ocean. Remember earlier when I talked to you about the threats to these oceans, overfishing, climate change, pollution, and so on? Using eDNA, we can scale up how we counter these threats. That's what eDNA promises. It scales, because boats go through these areas. Boats keep on sampling. I dream of this army, of this flotilla of on-water, underwater Roombas, vacuum cleaners. They pull in water, push it through filters, sequence it, and then send me a message with what they found. It's possible, right? These technologies already exist. It's not a distant dream. It's happening right now. We can find better, faster solutions. For example, scientists are already tracking which species appear and disappear under different temperatures. We can tell governments which species to help under different climate change scenarios and influence policy. We're building bigger reference libraries and sequencing more fish species so we can, from there, track invasive species as early as possible. So we can start quarantining, we can start countering these threats by these invasive species, even before we have visually seen these species. And we can track rare or threatened species and influence where marine parks should be established or where marine parks should be monitored in future. The future is now, and these technologies I talked to you about today, they're not happening in 10 years, they're happening right now. There's people in this room who are working in these technologies. Together, using these technologies, we can monitor, understand, and protect oceans better so that my children, your children, and their children can enjoy this beautiful, massive, enormous ocean for their lifetimes. Thank you.